Okay, I think we're in a good place to start.
Okay, let's start. You can hear me, right? Good. The sound is okay?
Yep, we're good.
Okay. Okay, let me put this down here. Right here. If I close this, it'll be okay. It's okay, right? Okay. Okay, today we'll talk about this ToF SIMS. And yeah, we don't have a big number, and I think about this and audience maybe, and I want to learn about the ToF SIMS. And this instrument, and actually our CAC tool have ToF SIMS like since beginning. We have old like ToF SIMS from the 5. That instrument relatively is old model, is not very user friendly, and especially to depth profile and to the sputtering. And this year, and unfortunately we get the fund, and through some factory, we get purchase this new ToF SIMS. This here you can see the M6, that is the latest model, and from ToF. And that is the first one installed in university in United States. I think there's another one maybe installed in the industry. Yeah, that is compared to the other one, is quite user friendly. But you know, today through the presentation, or probably you already you get training before and you learn something. And compared to other methods like SEM, like XPS, the ToF SIMS is a little bit complex, and the operation, especially for data analysis, compared to that is complex and complicated. But you know, that is ToF SIMS is a very unique technique, and some
comment next to that saying, but I don't know if he reached out about it yet.
should mute. Okay. So okay, Kitty, is there something? Let me know if okay. Okay, so this if you have any question, you can ask me, and after the presentation or any time during the presentation. And okay, so next I want to talk about the principle of the. Let me see why it didn't work. Okay, so talk about the principle and application and this, and during this, and then you probably have the knowledge about the XPS or EDX, and then you can compare, and ToF SIMS can give some unique feature, and some EDX XPS cannot do. And this name is like time of flight, and ToF SIMS. ToF SIMS is a time of flight secondary ion mass spectrum. First of all, you know, EDX is X-ray and spectrum, X-ray energy spectrum. XPS is electron spectroscopy. So this one is a mass spectroscopy. And so this is a secondary ion. That means they have a primary. So we use a primary to strike, bombard the surface, generate the second ion. So like a SEM, primary electron generate second electron, that SEM. This is use ion. That is the SEM electron. This is ion. Primary ion generate the secondary ion. And the secondary ion, and get the analyzer, we analysis what is the mass, and then get the mass spectrum, and understand what is on the surface. So why is time of flight? Time of flight is a method, is measure the time, and the ion fly from sample to analyzer. And based on the time, you can calculate the mass. So that is a method of analyzing. So this is ToF SIMS. And some people maybe know something, okay, and seems you have ToF SIMS, and some university like Stanford or some, and they have a nano SIMS. What's the difference? So this is they call the mode of the SIMS. There is two different SIMS. One is a static SIMS. One is dynamic SIMS, they call it. So like you talk about like Stanford, they have a nano SIMS, some SIMS fancy. And that SIMS is made by the Chemica. they use cesium and oxygen as primary beam and the spot surface generate second ion. This one basically is a very high dose. The high dose, they analysis, they are quickly to etch in of the sample. Actually, they collect information for several layers of this surface, and then they will and get the second ion. So this basically the yield is high. And of course, the destructive, very destructive on surface. So that is called dynamic SIMS. And our ToF SIMS from ion 12 or 5 is called static. This primary beam, the dose is low. You basically analysis only top layer. You see from here, the top layer get this. Top layer. So if you have a surface, you have some moisture or some contamination, you cannot get the information from your sample. You have to be remove this. But for this one, because the dose very high, even you have some little bit contamination, still you get a lot of information from inside. So that is dynamic SIMS, the non-SIMS, they can do a little bit better for the depth profile and for the mapping this. So there's a different type of this. So what we have is this. Of course, this one static SIMS also have advantage, and later we talk about. And this one advantage, so higher yield and better depth profile. So this is a static SIMS basically is the dose of this and ion, how much. Atomic surface density on the sample and surface look like and is like a 10 to the power 15, and this dose static SIMS is like this 12 or 13. That means the top layer can survive pretty long time. And this example, and on surface, the silicon surface, after static SIMS, ToF SIMS spot, and then we can get another STM image. You can see this area damaged, but most are still not damaged. So that is, first of all, this SIMS is destructive, but as a static SIMS, like ToF SIMS, their damaged surface very slow. The surface layer can survive a long time. And if you use nano SIMS, because those were high, then just maybe second, our whole layer is gone, and analysis second, third layer. So I give you a sense, like some people say, oh, why don't you use why didn't you buy the nano SIMS like Stanford? And they have that. But first of all, that is 3 times more expensive than our current ToF SIMS. Second is that one is not for surface analysis. Is for like depth profile, for some biosample, for the mapping. Is not like for not that surface sensitive like our ToF SIMS. So we more focused on the surface. Okay, this is a basic principle of the SIMS. So like surface, we use a primary ion to spot. And then we generate this ion. So this positive ion, negative ion, and this one is neutral. Actually, when the primary beam spot the surface, you get a fragment. You get not just like an atom, and some is the fragment, some bound together. So this is not all ionized. Only small fraction get ionized. Mostly is like neutral. This neutral, and then we apply electric field, apply the potential on the sample and get an analyzer. You see here the electric field. So only the ion can get analyzer. The positive ion or negative ion is different mode. If that is neutral, they just fly away, cannot get detected. For example, like a gold surface, like platinum surface, and even you have a lot platinum and gold. When you do this sputtering, you will find the mass peak for gold and platinum very, very low, because that is inert, that is noble, metal, they are not easy ionized. They just neutral and pumped away. And but for some like sodium, like potassium, and like lithium, like that one easy ionized, they very high count. For example, if your surface you use a finger to touch it, you get sodium, they can get a very high count for that. So this different element, so this yield totally different, can be order of like power 6, yeah, can be different. So okay, so we get this positive negative ion, and then we apply this and the electric field, so the positive ion can get here, can move. And then can move, you see there move the speed different because the primary ion gives this fragment, the energy is fixed. And then based on the mass here, based on the mass, so the velocity of the fragment different. So the light mass get detected first, and the heavy and get slow. And the first they get this one here, get this mass, and they get this mass, get this mass. So certainly you have with certain time, and then this all the mass can reach detect. So this time will define what is the mass we cut off. So this flight tube, that is the time of the flight. Okay, this is the basic principle of this time of flight. And this SIMS, we basically get 3 different this data. First, we can get a surface spectroscopy. And then like this spectrum, mass spectrum. And we get this, and we get not just element, we call molecular information. It's, for example, not just like atom, and some fragment like carbon, hydrogen, and there's some like 2 or 3, these elements bound together, like a polymer, like a fragment that bound together, this molecular information, and this mass can get. And secondly, that is quite sensitive. And this is even small contamination, small trace, small the dopant they can detect. Third is the mass resolution is pretty high. This is very critical. You see here is 27.97. This is 28.03. If this mass resolution is low, you cannot distinguish this. You think that is the same. Actually, it's different. So this one is the silicon peak. This one is from C2H4. So if you have need a very good mass resolution, and you can distinguish them. Okay, you know from this from contamination, surface hydrocarbon, this from silicon. So second is the surface image. And then you can choose what fragment, what ion you want to map. And then you can get this elemental information. And then you know the distribution based on this. And this get a quite better and resolution. This image, like elemental image, of course, you know the EDX, you can do the mapping, but you cannot do light element. So only the heavy element. So this one you can do all the element. And also the XPS is sensitive, is quite useful, but XPS cannot do the mapping. So this SIMS, they give you the unique point is they can see this distribution of the element is a quite high resolution like this. The third, the data type is depth profile. So you can spot and then analysis, and then you can get the certain element and how they change, get this along the depth, get the depth information. And based on this data, you can do the 3D and render and the 3D reconstruction, get it great. And this is the schematic of the SIMS, and this is primary beam. Basically, they use bismuth gallium, and in our instrument we use bismuth and the bismuth cluster. We can use this. And this side is spot. We have we can use cesium most for negative, and oxygen most for positive, and we also have argon cluster gun for the organic like polymer to spot. And this one can spot. You can use this to surface clean For example, you have a surface contamination, you want to see the underneath, and then you can clean surface. Or you can layer by layer to spot to depth profile. And this spot and this analysis, the analyze. And here show the mechanics of the depth profile. And most people think here is use the spot beam to create an array analysis center. And some people think about, okay, we analysis that. So that is for some, and like nano SIMS, like dynamic SIMS, you spot the area and you CGM, and all this ion and get to analyze it. They use a magnetic sector. They can separate the mass, and then the analysis. In that case, all the spot this ion get to the analyzer like this, the analysis. So basically use this method, the concentration are more sensitive because whole spot this yield, the analysis. And for ToF SIMS is different mechanism. So this color, you see this color is analysis, and white color is spotter. You see, when you do the sputtering, analyzer doesn't work. We do the analysis. We only, after you spot a layer and you get a new surface, and then when analysis, what is on the surface, and then remove another layer, and then analysis the surface. Is this one basically the profile? You analysis this surface, get this. XPS is the same mechanism, get this. So if you, each time your spot cycle is too long, you will miss a lot of information. If you make a small step, you have a better depth profile resolution, but you take a long time. So you have to be like a trade-off to, and consider is the spot time and how long time you want to spend on this. So that is ToF SIMS, the depth profile, basically this like this cycle. Okay, so all SIMS get the information, and this basically you need when you collect the data, you need to choose what pixel size you want to use. Commonly for the spectral, we use the 128 to 128. This for the mapping, we use 500 or even 1000 by 1000. Commonly is 500 by 500. So you choose this pixel. Actually, we collect. So each pixel, actually, at least they have one spectrum. Of course, you can change. Each pixel you can collect 2, 3, 5, or 10 spectrum. You can do that. Of course, it will take a longer time. At least one spectrum. Get this one. So when you collect the data, and then you get this. For example, you use 256 pixel by 256. You get at least 65,000 spectrum. Get this spectrum. And then this raw data you collect. And then you can choose certain peak, certain mass. And then you can see the distribution to the mapping. And then you can choose 2 or 3 overlay together, get this image. And then, so that is from the raw data, you can get the image to this certain peak. And then you, from total image for this, you see here different. You said the 1 pixel of the spectra is too weak, and I want to get more. So you can integrate this area together. They called ROI, the region of interest. You can choose this region, integrated all the pixels together, get one spectrum. And you can from here get another integrated, get another spectrum. You can compare from here to here, you get 2 good spectra, and then see the difference. So all this you can do like a post process. So This SIMS, basically, you can maybe collect data, you can spend just 10 and 1 hour. The process maybe spend 10 hours longer. But that is good, you know, you would use the software, another software to do the data process, not charge you. So you can use another computer to do the data process. And then basically you collect everything. Even during the collection, you forgot to put any peak, it doesn't matter, you have everything. Okay, so this is like a typical spectrum. And mass spectrum, you can see the peaks. Here's the carbon, hydrogen, CH3, the sodium, C2H3, C2H4, and here like lead isotope. This advantage, you can see the isotope, even the same element for the XPS cannot see the difference, but the mass spectrum can see isotope. That advantage is for some special element, for some and X sample, you can, for example, purposely put the isotope, use like and deuterium, like a carbon 13 or 14 to label certain area, and then use this mapping to see how the distribution of that labeled element. So these are mass spectra. So this is an interesting mapping image, and that is a real sample we collect. And actually, when we run this sample, like last 1 year ago, maybe 2 years ago, that time we didn't have this better resolution, and we use the old SIMS. That time we still can see the difference, but not the picture, the quality is not like good like now. And this is a perovskite sample. This one is 0.1% oxygen doped. This is undoped. So XPS, this low concentration cannot see the difference. And use the SIMS, we are not only can see the difference, we also can see this distribution of where is it doped. You see here undoped, there is an oxygen is very low. For this doped, you see this area is bromine, this oxygen, you see on the green boundary, and you can see this oxygen after the doped is much higher compared to this. So that is published data. That time published data is not that good. This after the publication we get. So this image, you see this green SEM image, also we can get, use the SIMS, we can get the surface, and similar like SEM image. So this kind of distribution, this and very high sensitivity and also see distribution, that is very unique, and only ToF SIMS can give. XPS, EDX cannot give this information. This is another useful feature is for depth profile we talk about. This is ITO on silver and on silicon. So we spot, get this, and after sputtering, you can see this indium, and this silver, and this silicon is. And then we can use the data, we can do the 3D rendering, and then this top layer, ITO, indium, and this silver, and this silicon. This is another sample. This is a multiple layer of the metal on the silicon we spot, and this is a crater. This crater, we can, this optical image, we can see this crater. And then this, after this depth profile, we map this area. We map this area, we can get this and a nice and the image, and then we overlay this different layer and put together and get this. Overlay this all the different. And after this sputtering, you will want to understand how we get these depths. For this crater depths, we have to use this profile meter. We take them out. That crater typically like 200 micron is easy to find. Use this optical and camera. And then find this area, we get the profile. And then we measure, we get, okay, this is 170. nanometer in this crater. And then we can put in the software, we can use a profile, this one, we can use this depth, change, convert to the depth from the time. And then we can get a different layer. And you see this depth profile, this, and then the 3D rendering. And then I always, that after I created the crater, and because that is a cross section, even that is not sharp, that is like a sloped, because different when you spot and you get this, and that is a sloped the side. And I also want to see this and see this cross section. I focus here, I get this. You can see the different layers, this copper, and titanium, and moly, and this silicon. And put together, you can see this cross section. This is a SEM mode from SIMS. SIMS also has SEM mode, and this doesn't have elemental information. From this one, you can get this and elemental information. Okay, so that is for depth profile and the mapping. And we have this instrument, we have several holders. This is a top mount. The sample we can mount here, and then we can use this clip or use a tape, double sticky tape. This mount and the sample and height have to be less than 1 centimeter. This is pretty high. But they use the top mount, have to be careful and not touch the lens. And so this is a back mount. This is more safe. And we use a backside mount the sample. We can mount like this 12. And here also we can mount the small sample here. And mount this one, they call the back mount and the sample holder. So this one is use heating and cooling. And this temperature range from the minus 180 to the 600. And this, we have a air-free transfer. So we can use a glass box for some battery sample. We can mount the sample inside here. And then put the sample holder in this box, this small box, and then use a small transfer can get out. And this box we can load in the load lock. And inside, after pump down, we can open inside. So that is the totally air-free, and you can transfer. Okay, I want to summarize this advantage and the disadvantage of this method of SIMS. And first of all, they can detect all the elements. Like XPS, it cannot detect hydrogen and helium, and EDX cannot detect light element, but this method can detect all the elements. So this isotope you can find the peaks, the trace, especially the ppm to ppb level, and very sensitive. Sometimes too sensitive, you can get much information there. So also high spatial resolution to the mapping, you can do the distribution for that. And then parallel detection, that is very useful, For some method like XPS, you detect 2 elements and 10 elements, total different time. And if you analyze 10 elements, you spend like 2 hours on 1 element less because in theory to detect. This one is parallel. Once you get there, you collect everything parallel and simultaneously. And you can spend like a half hour to collection. And you have everything. And after that, you can spend 10 hours to analysis. And that is save a lot of time, parallel detection. And the detailed molecular information, and especially for organic sample, and they get a big fragment. They can get like this, and the big fragment you can put together. You can give you the molecular information. You can also fragment mapping, and then go to molecular mapping. And the 3D, we can do the depth profile. We can do the 3D rendering. And then they can analyze all the samples, the conductive, semiconductor, and insulated, because we have a flat electron flutter gun we can use for insulating. And of course, your sample have to be solid and ultra vacuum compatible. We can analyze powder sample, but not like a liquid, like a gel, have to be and compatible with ultra vacuum. This is our knowledge. And this one, this secondary ion often highly depend on the matrix. They call the matrix effect. So in the different matrix, this yield can be different. So that is a very difficult to do quantification. Secondly, destructive. After this, because they get fragment come out after this sputtering, even that is a short time, your surface will be damaged. Some surface layer will be damaged. And then, so if you want to do quantification, you need a reference sample, the standard sample, have same matrix, you know and the concentration. Based on that, and compare with your sample, you can do this quantification. Otherwise, you just one simple sample, one spectral. You cannot just use this peak density to calculate this and the concentration. Okay, the data interpretation could be difficult. And because this is very sensitive, they have so many possibilities of combination. So you will get a huge data amount. So mostly you should need to focus on what is your element you have, and you focus there. You are almost impossible to label all the elements. You don't have to do that, but you have to label the major peak. You can do that. This is difficult. I said maybe it's time consuming, but that is, of course, and we use based our and the software we can label and check the major peak for that. Okay, this is a summary of this. The spectroscopy, you can get this identification of the unknown and the element on the surface. And you can do the mapping, you can label certain and the element, you can do the distribution, the mapping, and then you can do the profile. Okay, so that is my presentation and talk about the basic principle of the ToF SIMS, and hope you can get idea, understand what is ToF SIMS can do, cannot do, and in the future you have a sample, you can wisely choose, and from XPS, ToF SIMS, EDX, or anytime. And after this, even during the presentation or after that, anytime you can talk to me, and you have this project, so which method you should choose. Okay.